So we have been talking about vector spaces. The four fundamental subspaces. Okay, we have a matrix A. Okay, so vector space is not necessarily related to a matrix, right? So we have the definition of it. Independent of a matrix, we define the basis and spanning and dimension of a vector space and subspace and everything. Now, then we started looking at matrices, and we generated four subspaces for any given matrix, right? So if you have an A, Aij, M rows, and N columns, we talk about four subspaces. And you will certainly have questions about this in your midterm, for sure. So you have to make sure that you really understand this, okay? So we talk about the four fundamental the four fundamental subspaces. One, the column space. Two, the null space. Three, the column space of A transpose, okay, of A, A transpose. Four, the null space A transpose. Let's remember what these are. So one, so we call this CA, right? We call this NA. We call this CA transpose, or I also sometimes call this row space of A, right? And this is the left null space of A. So these are equivalent names for the same thing, okay? So let me just briefly remind you what these are. So column space of A is spanned, is a vector space spanned by the columns of A. Okay? So what do we mean? This is what we mean. So you have A, okay? So A is C1, meaning first column, C2, Cn. So when you say that it is spanned by the columns of A, what does that mean? Can someone tell me? What does it mean? The space is filled by what? Very good. Linear combinations of the columns of A. Okay? That's what it is. So you would say that this is like x1, c1, x2, c2, xn, cn. So any x in CA, okay, where this means x is in CA. Any x in CA is a linear combination of Cn. And this CA, this is a subspace of what? What is the bigger space here? So how many components does each C1 has? How tall is this? How tall is a vector? It's written here. Okay? M, right? This is, each column has a length M. So this is R M. What does this mean? This means M-dimensional real vector space, right? Okay. Okay. So, and how many columns does it have? It has n columns, okay? So, what would be the dimension of this subspace at most? N, right? Of course, if n is greater than m, can it be greater than m? No. So if you have, so since this is m by n, okay, this you have n vectors here. If m is greater than, anyway, this is, I don't want to, there is nothing magic here, okay? Just do not confuse the number of components of a vector with the dimension of the space it belongs to, okay? So the number of vectors that spans it, number of linearly independent. So what is the dimension of a column space? What is it? So this is how we wrote it, right? So you say y is equal to, let me call this, I'm sorry, let me call this y, okay, so we don't get confused. Y is equal to ax. This is a short way of writing this, isn't it? So this is, A is C1, C2, Cn, and this is x, x1, x2, xn. So you multiply A with x, and you get a linear combination. So this multiplication corresponds to taking a linear combination of the columns of A, and you get this, okay? So what is the dimension of this column space of A? What would that be? It would be the number of linearly independent columns of A, right? So the dimension of CA is equal to number of linearly independent columns of A. Okay? So what is that, by the way? We have another name for that. Rank, yes. So, which is the rank of A, right? Let's just write here something very easy. So this is our A, let's say 101, 202, 11, 101, 402, okay? So how many vectors do I have in the columns in the column space of, so what is the spanning vectors of the column space of A? What are they? 1, 2, 3, right? You have 3 columns, C1. So this is C1. This is C2. This is C3, isn't it? So that you know what corresponds to what, okay? So this terminology corresponds to that. So column space of A is spanned by these 3 columns, okay? how many linearly independent columns do you have here? Of course, it is at most 2, right? It cannot be. So since this is a 0 column, it is certainly not linearly independent. So you cannot count it as a linearly independent column. A 0 vector is just 0 vector. So you will just look at these 2, right? So looks like they are linearly independent. So this has 2 linearly independent columns. So what would be the dimension of the column space of A? It would be 2. Of course, since this is just very simple matrix, we are able to just look at it and see it. But how do you do it? How do you determine the rank? And how do you determine which vectors are linearly independent, all those? How do we do that? Gaussian elimination, right? We perform Gaussian elimination, and for free, what do we get? No extra charge, LU decomposition, right? When you perform Gaussian elimination, all you need to do just write on the side what was your multiplier. Then in the end, you just fill in your L matrix. So you have LU decomposition, it comes out free of charge, and you have A is equal to LU. So this is the summary of column space. So any question on this? Any quick question? I will come back to this, and I will continue what I started during the last lecture, how to compute this basis for these subspaces systematically, which you will need in your exam, okay? So let me continue here. Oh, let it stay there. Let it stay up there, so we can refer back to that. Now, what is the second one? Null space of A. So, 2 null space of A. So what is null space of A? Null space of A here, the subspace is defined as a space spanned by the columns of A. So it is explicit. We see it, okay? When we look at A and the columns are there, we say, okay, so these guys, they get together and they span the subspace. But when we talk about null space, as you know, is defined as the vectors X that will satisfy this. So the X is that when you multiply A with them, they will be equal to 0, okay? So how do you find, so say that the X is the solution set of AX equal to 0 spans the null space of A. Okay? So let me take that example. A is equal to 1, 2, 1, 4, 1, 2, 1, 4. By the way, what is the dimension of null space of A? What is the dimension of null space of A? N minus R. So this is 1, 2, 1. This is also 2, right? So the X will have how many components? The components here will be equal to N, right? So it is X1, X2, X3. Okay? So this is N. So if this was a full rank, then what would be the only vector that has a solution for this? Okay, so this is AX. So how many components do I have here? 4, right? M components, okay? So do not get confused on these things, okay? So you multiply 4 by 3 matrix by 3 by 1 matrix, okay? 4 by 3, and this is 3 by 1. So these 3 is canceled, so to speak. So the result is 4 by 1, okay? So the dimension of null space of A is equal to n minus r, okay? And the dimension of column space of A is equal to r. So how many, so what is the dimension here, since we said that for that matrix the rank was what? What was the rank of that matrix? This rank of this matrix was what? 2, right? Everybody 2, right? Do we realize it, everybody? Okay. So since it is 2, and what is n here? 3. So for this example, dimension of null space of A. So you have several questions in your homework set on this. And you know that I promise you that I will ask some of the questions in your exam from your homework set, right? Is equal to, so 3 minus 2, which is equal to 1. Okay. So we will look for one non-zero solution here. Then we are done, right? If we had 2 here, then we would look for 2 non-zero linearly independent solutions. So we need to find one. Can you just tell me one? 0 doesn't count. I said non-zero. 0 is always, okay, 0. 0 is in every vector space and subspace and everything, right? So that doesn't count. It counts. It's very important, but it's already there. So what is this? So what should I pick, x1, x2, x3, so that I have this? So easy.
0, 1, 2.
Exactly. Yes. So x is equal to 0, 1, 0. So the null space of A is spanned by what? By this vector, right? So the null space is spanned by 0, 1, 0. That's it. Spans null space of A. So here, what spans? I'm just putting the side by side, you can see that. What is the spanning vectors here? It is explicitly, it is in the question, right? 1, 2, 1, 4. And the other one? 1, 2, 1. So these are also a basis. Why? Why is it a basis? No, of course. Linearly independent, yes. Also, so they span the subspace and they are linearly independent. Therefore, so they are equal to R, right? The number of vectors, spanning vectors, if they are equal to R, they are also linearly independent. So all these things are equivalent. So you are right. Okay, so spans, this is how you are going to write your answers. Spans is a basis that spans column space of A. So you see the difference? When we talk about column space, the basis is the columns of A. When you talk about null space, it's not explicitly anywhere. You have to solve it, right? You have to get it. Okay, so the third one, what's the third one? So the null space of A transpose. So 3 meaning column space of A transpose, also which is row space of A. So what do I mean by this? What I mean by this is this, okay? It's easier to understand. First look at it as a row space of A. So it is, you have A, M by N, okay? You multiply this with X transpose, you obtain a Y transpose, okay? So in other words, you have row 1, row 2. How many rows do I have? Row M, right? So you multiply this with x1, x2, xm. What will this give you? x1 times r1. So this is what? Is this a vector or scalar? x1. x1, just this number. This number. Scalar, right? Please. r1 is a row vector. So we used to write arrows on these, okay? We are not writing this because it should be clear to any linear algebra student or any engineering student from the context what it is, okay? Otherwise, we could just keep writing all these arrows, okay? So xm r m. So if you consider all linear combinations of these rows of A, you obtain the row space of A. Okay? So what do we say? What is the way to say this? We say that row space of A is spanned by the rows of A, right? So column space of A is spanned by the n columns of A, and row space of A is spanned by m rows of A. It's so simple, right? So there is nothing to get confused about. So these are not difficult or confusing or anything. Just very carefully look at it and do not think it is something difficult or confusing. It's very simple, okay? So also I said we look at it also as column space of A transpose, okay? Since in this course we always talk about row operations and we talk about columns as vectors, right? So we could as well talk about column operations and we could talk about row vectors. They are equivalent. You could do everything you are doing with the previous terminology. You could do the same thing with other terminology, okay? So in order not to work with row vectors, etc., we could as well say that we talk about A transpose. So if you take transpose of this, what do you get? So take transpose of X transpose A is equal to Y transpose. What do you get? A transpose X is equal to Y. Okay? So let me write this in parallel here. So in that case, that would mean that you have R1 transpose, R2 transpose, Rm transpose multiplied by x1, x2, xm, which is again x1 R1 transpose plus x2 R2 transpose, etc. xm Rm transpose. So you take the matrix, take the transpose of it, and in the new matrix, the rows of the matrix become columns of the new matrix, right? And you apply what we did there. That's all. Okay? So there is no difference. So what do we say? The dimension of column space of A transpose is equal to what? Is equal to number of linearly independent what? What? Very good. Who said that? Good. Which is equal to? That's equal to what? Which is equal to? What? Rank of A. So rank of A is the same as rank of A transpose, right? It doesn't change. So that's the beauty of it. So rank equal to rank A. Okay? Yes? Arrows were not necessary here, and they are not necessary here as well. I was just making a point when I put those arrows. So from the context, it is clear that I said these are rows of A. So therefore, but you could write here as well, no problem. But arrows will not save us. We should know what they are. Okay, we should understand. The context very clearly defines that. Okay, let me look at that example there. Okay, so let me see. I will just use this area and this area to do that example. So let's find two linearly independent rows. We said all of the rows, right? They span it. What is the basis? So basis was what? Who's gonna tell me that again? Excellent. Yes. The vectors that are they span the subspace. They span the subspace means what? They span the entire subspace. Meaning they do the job all these four rows do, right? And they are linearly independent. So that means their number has to be 2, since the rank is 2. We looked at it, we said, okay, you have 1 0 row, 0 column there. Therefore, rank is 2. When you are looking at the rows, there is no row rank or column rank. Rank is just one number, okay? So row rank is equal to column rank. This is a beautiful result again in linear algebra, okay? So you can have a matrix with 1 billion columns and 2 billion rows. Okay, so if you didn't know this, that the column rank and row rank are the same, you would first find the rank of 1 million rows, and then you would 1 billion rows, and you would look for also a rank for 1 billion columns. But you don't need to do that. Row rank is equal to column rank. So number of linearly independent rows and number of linearly independent columns is the same number. Okay? So you have to, so can somebody tell me two linearly independent rows there? Let me write them here. I will take the first one. Somebody tell me another one. 402, right. Do I need to look for another one? No. So of course I take transpose of these, okay, because we want to stick with. So this is a basis for the column space of A transpose, okay? Is this the only basis? Can I have other bases? Can I? So give me another example, for example. What would be another basis? 202 and 402. Another one? Minus 1, 0, minus 1, and 2, 0, 1. How many? Infinitely many. So the number of vectors, we know it, it has to be the same as rank, but you can have infinitely many bases, okay? After your exam, we'll start even more beautiful topics, and we will talk about orthogonal bases and how to create orthogonal bases. We give you a number of vectors, and they are just junk. They are not orthogonal. What is orthogonality? I'm going to tell you today. Then how can you generate an orthogonal basis that span the same subspace as those vectors are spanning, and they are orthogonal? Okay, how to do that? It's very simple, very nice. Okay, so we have one more left. So what is the dimension of this? Did we write this? So the dimension of, okay, we wrote this here. Okay, this is a subspace of what? How many components does each vector have here? Okay. This is R as how many? N, right? Okay. R, N. So when we look at it, so you have this null space. Okay, null space is a subspace of what? R, N, right? So that was subspace of R. Did we write it? Yes, Rm. Okay, this is subspace of Rn. So the null space of A is a subspace of N, meaning each vector in this one has N components, right? So it is a part of Rn. So it's, you have an n-dimensional real vector space, and the vectors in the null space of A, they have their own little or big or whatever subspace within that big space. Now, when we talk about, so that these and these two, sorry, yes, null space of A and column space of A transpose, they are subspace of Rn. Did I say something else? I thought I said the other one, okay? Now we have one left, and that is, let me erase this one here, or I want to keep that. Let me erase this here, so that we have 4 subspaces in 4 blackboards. So the fourth one is the left null space of A, which is the same as null space of A transpose. Okay? So what do we mean by this? You have your A, okay? You multiply this with X transpose, and you get 0. So again, that duality that we had there, or unduality that we had there, you had the column space is spanned by the columns of A, but null space of A is not explicitly spanned by anything. You have to solve it through that equation, right? So we have now column space of A is spanned by the columns of matrix A. Now we talk about left null space of A. Okay, this is spanned by what? So x1, x2, xm times row 1, row 2, row m, right? Equal to 0. So you find vectors that they are eaten by this matrix. When you multiply them with this matrix, the result is 0, okay? So that's the null space. So let's look at that example again. So you have, what is the dimension of? Dimension of course, here you take transpose of both sides. Then what do you get? A transpose X is equal to 0. So does it look the same? So this is, if you look at it as left null space of A, this is what you mean. Or you can look at it as the null space of A transpose like we had up there. So they are exactly the same thing. Okay. So what is the dimension of? The dimension of null space of A transpose is what? Is M minus R. Yes. So they complement each other. Meaning, in an m-dimensional vector space, if you take any random vector, it's either in this or that, okay? It's got to be somewhere, okay? We will talk about today how do we project a vector into a subspace as well, okay? Let's do this example. So this is a subspace of R M. Why is that? Because these x's have m components. Okay, example 1, 0, 1, 2, 0, 2, 1, 4, 0, 2. Okay, for this example, what is the dimension of null space of A transpose? Can you tell me that? So this is, the rank was 2. What is M? M is 4. Rank 2. Okay? So we have to have 2, right? So we are going to have what? What will be the result? So this is 1 by 4. This is 4 by 3. The result will be 1 by 3, right? So this is going to be 0, 0, 0. Okay? So tell me, so you have the rows here. How can you find something here that will make 0? Give me one solution. Very quickly, okay? Let me put it up here so everybody can see. It's very easy. Obvious solution, like you did there, up there, okay? What's the obvious solution here? 0, 1, 0? No. We are multiplying from here. Okay? I don't understand Turkish during the lecture. Okay? 1 minus 1, 1 minus 1, 1, 0. Okay? 1. So Yes, it does that. Another one, very, very simple one, 1, 0, minus 1, right? Another one, so many you can find very easily, right? But how many are we going to look for? That's why you need to do this calculation first. If you found, are these linearly independent? Can you obtain, how do we know if they are linearly independent or not? We don't need to always write that formula, right? So if you look at this here, can you obtain one of them as linear combination of the other one? So they are linearly independent. So therefore, a basis is 1, minus 1, 1, 0, and 1, 0, minus 1, 0. Are these a part of this matrix? Do you see them here? No, right? They are not explicitly a part of the matrix. So they are obtained by solving that, okay? So this is a basis for null space of A transpose. Let me continue. Why don't you continue? Do you need a break here? Let's continue so that I'm going to tell you how to do this systematically. Or let's give a 5-minute break and then we'll continue because we need to do some work today, okay? Okay, let's break for 5 minutes. I want you back here at 1:21. Now, how to compute these bases for subspaces, okay? So we know now what are the subspaces. What are the 4 subspaces? If I give you an A, what are the 4 subspaces, right? By the way, if the matrix was a 4x5 matrix and it was just all zeros, what would be the null space of that matrix? It's a 4x4 matrix. R? R what? And there is no R direct. What is R? 4, right? Who said 4? Good. Okay. What would the column space of A? What would be the column space of A? It would be the 0 space, right? It's a subspace that has only one vector. We call it 0 space, okay? What is the dimension of a space that has only 0 vector? 0, right? Okay. What would be the row space of that matrix? It's again 0, right? And what would be the left null space of that 0 matrix? It would be R4, right? It's the same. Okay, if the matrix is an identity matrix, it's 4x4, it's identity matrix. What would be the null space? I'm not even writing those, right? So this should be, so if I have an identity, my matrix A is equal to identity, so 1, 0, 0, 0, 1, 0, etc. So what would be the null space of A? It's 0, right? It's the opposite of the example before, etc. Okay. So the way we approach determining of all these subspaces and their span and everything is our good old Gaussian elimination, okay? So let's say we have A is equal to, so how to compute basis for subspaces, okay? So let's say A is equal to 1, 3, 3, 2, 2, 6, 9, 7, minus 1, minus 3, 3, 4. Okay? So what do? We perform Gaussian elimination, the good old Gaussian elimination. So how do I kill this? Okay. So what should I do? What is the multiplier? 2, right? So L21 is equal to 2 over 1, 2 over 1. So multiply the first row by 2. So this is equal to 2. Multiply it by 2 and subtract this from the second row. So you have 1, first row stays the same, 3, 2, this is 0, and this becomes 0, 3, 3. And I want to kill this one now using this pivot row, right? So what is L31 is equal to minus 1 over 1, which is minus 1. So multiply this with minus 1 and subtract it from here. That means add the two things together, right? So you have 0, 0, 6, and 6. Okay? So we are finished here. This is our first pivot column. First pivot column. Okay? We are done with that. Now we go to the next column. To take care of what? To take care of the second column. Okay? So how can we use this as a pivot equation? Second column. Why not? Because it is 0 here, right? Then what would we do in that case? We would say, okay, let me go to the next row. But we go to the next row, it's again 0. If it was non-zero, if this was non-zero, what was I going to do? I was going to exchange that, right? So I cannot exchange. So what do I do? So this, I go all the way, so I cannot use this. What do I call this? This is called free column. Free column 1. So we are, okay, as we progress, we are now finding out all the secrets of our matrix. We are just decimating it, okay? So let me continue. So when I come here, okay, this is not 0, good. So this second row has a non-zero term. I can use that to kill this one, right? So what is L3 L3 3 is equal to what? But look, when I want to kill this, I call this L21, right? I want to kill this, I call this L31. I want to kill this, I call this L21, L32. I want to kill this, I call this L33. L32? L32. Yeah, L3. Anyway, so what is the result? 1, 3, 3, 2, 0, 0, 3, 3, and this is going to be 0, 0, 0, 0. Okay? So this multiplier L, let me call it for the time being. When we write L matrix, we will see that. Okay? So I took care of this one. This is my second pivot column. I go to the next column, right? I took care of the first, second, I didn't do anything. It was taken care of by itself. I took care of the third one. Now I go to the fourth one. I see that there is nothing to take care of, right? So therefore, this is also a free column. So I have here free column, and this is first pivot row. Okay? So what is the rank of this matrix? How do we know this? Easily, in this case, you have 1, 0 row, so you have 2 linearly independent rows, right? It is 2. Also, we have 2 pivot columns, therefore it is 2. So row column and the rank of the column and rank of the row is of course the same. Okay? So here, what we say is that the first column and third column of this matrix are pivot columns. Therefore, the first column and third column of A also spans the column space. Okay? And these are the free columns. Okay? So, since C1 and C2, let's call this U. In U are pivot columns. First C1 and C3, right? C1 and C3. First and third columns span CA. Okay? So and then how do I compute? So this is that's what do I mean by this is the 1, 2, minus 1 and 3, 9, 3. They span the column space of A. Okay. What would that mean? For example, do I believe this? Of course I do, but let's also verify. For example, I should be able to obtain the other 2 columns as linear combination of these 2, right? So can I obtain this as a linear combination of that? So this is, so let me write, so can I find 1, 2, minus 1 times alpha plus 3, 9, 3 times beta is equal to 3, 6, minus 3. So what would I obtain from here? Alpha plus 3 beta is 3. 2 alpha plus 9 beta is 6. And minus alpha plus 3 beta is minus 3. So if I add these 2 together, from these 2 I have 6 beta is equal to 0, right? 0, that means beta is 0. If beta is 0, then alpha has to be 3. Alpha is 3, so this is satisfied. And beta is 0, alpha is 3, this is satisfied. Beta is 0, alpha is 3, this is satisfied. So it satisfies all 3 of them. Okay? Similarly, you can find a linear combination of these 2 that will give you this one. So therefore, the entire subspace of entire column space is spanned by these 2 columns. How about the null space of A? Okay? Null space of A. How do you find that? For null space of A, you just need to solve. See, A is LU, right? So AX is equal to LUX is equal to 0. Since L is always a lower triangular matrix with ones on the diagonal, that means this is invertible. Therefore, this means UX is equal to 0. So AX is equal to 0 if and only if UX is equal to 0. Therefore, we don't need to go back to A for the null space. We just look at that one, okay? So let's look for UX. So you have 1, 3, 3, 2, 0, 0, 3, 3, 0, 0, 0, 0. By the way, we can further continue this, okay? This is called echelon form, okay? Meaning it's like a staircase. You have sort of below diagonal. This is not a rectangle. This is not a square matrix. Therefore, you have zeros below as much as possible. But we can also make 0 above these columns as well. For example, we can just continue this one and say that I subtract this row from this row, and what would I obtain? 1, 3, 0, minus 1, 0, 0, 3, 3, 0, 0, 0, 0. I can also divide this by 3, and I would obtain 1, 3, 0, minus 1, 0, 0, 1, 1, 0, 0, 0, 0. So this is called row reduced echelon form, okay? So it is now much easier. So you have here, which were the free columns? So these were the free columns. So you can just take these, and the other one, as you see here, identity is hidden here. You see if you have a first column of identity matrix here, and the second column of identity matrix here, right? So you have the others here. Okay. I don't want to spend any more time on this because I'm going to explain this now in most general form. So I will give you some formula. We've developed some formulas. I don't want to get more back down on this one, and let me start explaining to you the general methodology to obtain the basis vectors for all these 4 subspace for a given matrix A. And we will do more examples during that problem session we will have for the time you choose. Okay. In general, you have an A matrix A with m rows and n columns. And this A, as we know, can be written as A is equal to LU. And this L has a form of L11. L means lower triangular matrix, right? L11, 0, L21, L22. And U, I will tell you what is this partition. U11, U12, 0, 0. So this is the most general form you can have in L and U, okay? Of course, there is one thing we have to be careful. I had an example like that in the first quiz. What was it? Is this kind of factorization always possible? No. So, special case. You might have to multiply A by a permutation matrix P, and you say PA is equal to LU, right? In another case, okay, here, this U11 is an R by R matrix and is non-singular. But as we see in this example, it doesn't have to be like that. Sometimes you might have this U11 could be distributed over the columns, okay? So what do we do in that case? That is our second special case. So this is special case 1. Special case 2 is you might have to multiply A by a Q, okay? These are the special cases. I will give you a handout. I analyzed all those things here, okay? So now we will study the subspaces and bases of subspaces starting from LU representation, let's say, or the composition of A. So how do we obtain the basis for subspaces? Is there any question so far? So what am I trying to do here? What am I trying to do here? So it's very important that we pay attention. So we define what the subspaces are. And when you define a subspace, we will do things with those subspaces, right? So what determines what is a subspace? The basis vectors, right? We need to know what spans those subspaces. What are the basis vectors that span those subspaces? So now we are talking about how to compute them. After all, whatever we do here in this course, we always talk about how to compute them, right? In a very simple manner. Okay, so let's now talk about 4 subspaces one by one. So we first talk about here, one null space of A, okay? Null space of A. So how do we obtain a basis for null space of A? As I said, A, so we are assuming we are not in special case. So we are in the regular case, okay? So U11 is R by R, and it is non-singular, okay? And LU decomposition is possible without first changing rows. So you have LU. Null space of A means, what was it again? The solution of this system. The x's, the set of all x vectors x span the null space of A, right? So AX is equal to LUX, which is equal to 0, okay? Since L is invertible, this is equivalent to saying UX is equal to 0. So let's look at U. So it is U11, U12, 0, 0. X1, X2. So we partition the matrices, right? So how many rows do I have here? R rows. And how many rows are left here? How many rows did I have in A? It's just A is M by N, right? So it is M minus R, okay? So this is how many? So this is R, this is N minus R, and this is R, this is M minus R, okay? Good. So this is N dimensional. So this is equal to 0 means U11 X1 plus U12 X2, and this is 0. So we want this to be equal to 0 vector. So from here, what do we obtain? U11 X1 plus U12 X2 is equal to 0. Or if you solve for it, X1 is equal to minus U11 inverse U12 X2. So X1, these are pivot These are coming from pivot columns. These are free columns, right? So what does this mean? Let's talk about this. What does it mean? Okay? Like in that example, so if you had this column as well here, let me just change it so that, okay? In that example, I was trying to explain something else. So if it was like this, okay, these are, you see here, this is U11, like identity here. So these are the pivot columns, and these are the free columns. So I can pick the free column, anything I want, right? There is, I can pick it, any other than 0, of course. You shouldn't pick it 0. So what this is telling me is that, it's telling me, Davut, you so nicely worked out your problem and you performed LU decomposition and everything. So you made my job easy. This formula is telling me. You can just take x2 anything you want, okay? Each time take it something linear independent of what you took before. How many can I take, by the way? How many linearly independent x2s I can pick? How many? Okay, I can take it like this, right? I can first take this. So then what can I take? These are x2s, right? Then what can I take? Right? I can take them every time. These are free. Freely I can pick x2 as I wish, right? And how many am I going to have? M minus r of them, right? So what do I pick? I just pick identity. I just pick M minus this identity matrix. M minus r dimension identity matrix, I can pick them, right? So instead of solving for each x1, I can just make an x1, okay, like a matrix. I can solve for all of them altogether, right? So I can say x1 is equal to minus u11 inverse, u12, and this is just identity, okay? So what is my basis then? The basis x is equal to minus u11 inverse, u12, and you have, that's it. Who understood it? You understood it. Who else? 2. Come on. Okay, where did you get stuck? Ibrahim, I thought you understood it. Okay, where did you get lost? Yes? Yes?
And there is R and M minus R.
M minus R, yes.
Toplamı M.
Absolutely, yes.
Yukarıda da toplamı N oluyor.
This is N, this is M.
But square matrix.
This is square matrix, right? A is not square. A is M by N. We are not talking about square matrices. For square matrices, we don't talk about that much of subspaces, okay? Okay, this is M by N matrix. That's what we are talking about, right?
Can we apply non-square matrix?
Yes, yes, we can. Absolutely. What does it mean? That's why we had that conversation there. So what are you doing here? What is LU decomposition means? Let's just clarify that first. Let's say I have okay, this is my matrix A. Let's perform LU decomposition on this one. Okay? So what am I going to have here? So twice this is, so this is going 1, 1. This is going to be 0, minus 1. It's going to be 0, 0, right? So this is U. So how do I go back from this to this? Okay, I'm just keeping this very brief example so that we clarify this. So I have here one, 1, 0, minus 1, 0, 0. Okay, Abdul Fattah. So what do I multiply this matrix with so that I go back to this one? So what did I do here? So I should have something that, so this is, okay. Let's see what happens. If I multiply this with this, what do I have? 1. Good. If I multiply this with this, I have 1. Okay? So I'm just doing it this way, okay? So 1, 1. So if I multiply this with this, what do I have? 2. If I multiply this with this, what do I have? 1. Now, what should I multiply this so that I obtain this one? This is 1. Right? So multiply this again. 1 and 1. So this is L and this is U. So this is the most general form. So in some cases, you will not have U1, 2. Okay? This is the most general form you have. Okay? Sometimes it will be only this one, right? Like we did in the square case. Sometimes you will have this. Sometimes, most of the time, you will not have these 0 rows. Okay? Sometimes you will not have this. Sometimes it's going to be like this. Okay? Okay? I hope this, probably all of you were somehow stuck with this, that suddenly this guy started using LU decomposition for a rectangular matrix. What's going on, right? So this is L and this is U. Are you convinced now? Okay. So can I now go back to what we did again to review it? You look puzzled. Did you understand that one? Did everyone understand? Can you carry out this LU decomposition? You remember how we developed LU decomposition? So we first carried out our Gaussian elimination, and we said that all those steps we did, let's now go back one step at a time, okay? And multiply those matrices, not going forward, but going backward. Going forward, it got messy. But when we were going backward, it never got messy. You just had those multipliers that you obtained during your forward elimination. Just come and just put them here. That's it. It was so simple, okay? Okay. So what I said is that since we can carry out Gaussian elimination for every given matrix, it is square or rectangular, singular, non-singular, every matrix is capable of LU decomposition. Okay? Except we have one exception. What was that? You might need to do row exchange. So in that case, you first multiply it with a permutation matrix so that you do that exchange, and then you carry out your LU decomposition there. Okay? That was the case. We said that, okay, because all these bases for subspace are very strongly related to this L and U. You will see that they are there, okay? So when you carry out this LU decomposition, it is much more than trying to find solution of system of linear equation. It reveals everything about your matrix and the subspaces. That's so beautiful. That's why I want to give this to you, okay? This L and U has so much hidden in them, and they are exposed to us. They They just expose the entire subspaces to us. That's why we are going through it, okay? So we said that I'm looking for four bases for four subspaces, four fundamental subspaces of A. What are they, Ibrahim? Again, let's count them together. Space of A, null space of A, A transpose, which is also left null space of A. Yes. So we want to see what are the bases for all these four subspaces. Okay? Good. I said that, okay, let's consider those. Let's assume that we first carry out LU decomposition so that we bring our matrix in a standard form. So it is put in front of us as nicely, has an L part, it is lower triangular, another part, it is upper triangular as much as possible, okay? As much as possible. That's what it is. So we said that there are two special cases. We will, after we take care of this in 10 minutes, we will talk about those, okay? So I said, let me first look at the first null space of A. So null space of means Ax is equal to 0. The X is the vectors X that satisfy Ax equal to 0. So how many, the question here is how many linearly independent X vectors I can find, okay? When I find those, how many? It is, how do I know that? I know it from the rank, okay? I already, since I carried out LU decomposition, I know the rank of the matrix. It's R. So what is the dimension of the null space? I know it already, right? It is n minus r. I already know it from LU decomposition. So n minus r, I know. So I'm looking for n minus r linearly independent vectors in R, M, so that Ax is equal to 0, right? Is it clear now? We just carry out this multiplication, okay? So I partition this based on the rank. So I say, okay, this is U11 is a non-singular matrix. This is R by R, so this block matrix is such that this is R by R, and this is R, and this is N minus R. N, no, N, I was wrong there. N, right? You are multiplying it, like this is N minus R, okay? This is N minus R. So please correct it, N minus R. You can always make this mistake, it's just, as long as you know what you are doing, you are not gonna get confused, okay? So, we can pick, after this, what did we find out? We found out that, okay, this is U11 equal to 0, and you have one equation. Here, what it's saying is that you have x1 is equal to minus, you just solve this, right? From here, you take this to the other side, okay? U11 x1 is equal to minus U12 x2. So when I do an example, you will see it more clearly. Then I multiply with inverse of U11, both sides, to obtain this one, right? So you can pick x2 freely, okay? What is the dimension of x2? It is n minus, it is a vector with n minus 1 elements, okay? x2, the lower part of x. So I can pick it any garbage I want, but why should I pick it garbage? I just pick it 1, 0, 0, like 0, 1, 0, 0, 0, 1, etc., right? So that I have an identity there. So if I do that, this becomes, this is, okay, let's correct this. Okay, anywhere else? Now, who understood it? Did you forget it? No, you understood it before. So after I explain it again, did you? Okay, let me do an example. Hopefully it will be very clear, okay? Let's do an example. Unless you do it with your own hand, you write it today when you go home or your room, you will not learn this, okay? This is a must. I tell this to my children. I have 7 children. I kept telling them all their lives. You have to, when you go home, that day's lecture, spend half an hour, redo it, okay? Unless you write it, not when you are listening to me, but by yourself. You do it, you work it out yourself, you will never learn it. So, let's say I have an example where A is given in LU decomposed form already, okay, -1, 2, 1. This is L, and you have 2, 1, 1, 1, -1, 2, 0, 1, 2, -1, 1, 3, 0, 0, 0, 0, 0, 0. Okay? So what is the rank of this? What is the rank of this matrix? Do I need to tell you that? I give you this and this is the rank. So it is 2, right? How do you know that? Here, rank of the matrix, this is, okay, this is a square matrix. So rank of the matrix is determined by U. So last row is 0. So you have 2, and you see here that this first part is. So therefore, how do I do the partition? And I do the same partition here, right? So this is, so L11 is obvious, right? L11, U1, etc. So this is L11, 0, L21, L22 times U11, U12, 0, 0. Could I have a case? Do you think what I wrote there is the most general form? Could you have something else that maybe, so all these I wrote. I said this is the most general case. Could I have like, why not I have something else here? Let's say I have a 1 here, then I have, so, is that possible? Abdul Fattah? Do you think that would be possible? No. Why? Obviously, that row would be linearly independent because all these things, it would be, so I should include that here as well, okay? It would come also as a part of this, isn't it? Because that vector can never be a linear combination of these first R vectors. Therefore, this necessarily has to be 0, okay? If there was something, if there was a 1 here, let's say, okay? Then I could just make this, right? This would be U11 and this would be U12. There wouldn't be any 0 rows, okay? So therefore, this is 0. Okay. Yes? Excuse me? Which one are you talking about? Here? Yes. Yeah, they correspond to here. Yeah, this is L11. This is L21. This is L22. Okay. This is, so U11, U12. Right? So I did it so it's obvious. Okay. Okay. If there was a 1 here, let's say, then what would be the rank of this? 3, right? The rank would not be 2 anymore. It would be 3. Why? Obviously, this is a linear independent column, isn't it? Because there is no other element here that can kill this. Yet you can obtain this as a linear combination of the other numbers, right? So therefore, if there was such a thing, it then would be in the form of U11, U12, since this is a rectangular matrix. If it was a square matrix, it's a different thing again, right? Okay, this is the most general form when you have a rectangular matrix. Okay, if it's a square matrix, you can still have U12. Why? Because it can be a singular matrix. Okay? Is it clear now? Okay, good. So the basis for a null space of A is spanned by the columns of this X. Okay? So X is equal to minus U11 inverse, U12, and I, N minus R. So what is it? N is 6, right? 6 minus 2. So it is I 4. So what is U11? U11 is 2, 1, 0, 1, right? U11 inverse. Let me just give you this simple formula. You can derive it yourself. If you have A is equal to A11, A12, A21, A22, A inverse is equal to 1 over A11, A22 minus A21, A12 times, you just switch these and switch the sign of these. Okay? If you multiply it out, you will see it. It gives you identity. Okay, so what is U11 inverse? This is 1 and 2, 0 and minus 1, right? And you divide it by 2. Okay? So let me just do it here. U11 inverse U12 is, okay, let me just, 1/2, 1 minus 1, 0, 2, and U12 is 1, 1, minus 1, 2, 2, minus 1, 1, 2. That is equal to, this is not 2, this is 3. Okay? Are you following? So this tells you that, what does this tell you? Multiplying this here, okay? First row, okay? You multiply the first row by 1 and subtract second row from the first one, right? So you obtain what? Minus 1, 2, minus 2, minus 1. And this one tells you that just multiply the second row by 2. So that is 4 and minus 2, 2, and 6. And we should also multiply by 1/2. Okay? So what did we find now? X is, the matrix X is just what I have there times minus. Okay? So can you read that for me, Ibrahim? Who is going to read that for me? Abdul Fattah. So it is minus 1/2. Then this is 1. This is minus 1. This minus 1/2, right? Minus 1/2. And this 2, this minus 1, 1, 3. Okay? And this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay? So our claim now is that A times this matrix gives you 0. For every column, you just take it and multiply with A, you get 0. Do I get that? Okay? So for example, can somebody, let's do it together. Let's multiply now first row. If Ux is 0, then obviously multiplying 0 with L will give you 0, right? Yes.
Did we multiply the -1?
We did. We multiplied the first row by 1 and second row by -1, added that. So we subtracted the second row from the first row. That's what we did. Okay? Let me see if we made any calculation error. So it is 1/2. So we should multiply this with -1, right? It was minus U11 inverse. You remember it's like this. X is minus U11 inverse U12, and this was I and minus R. So this minus, we ignored it. Okay, so this is 1/2 minus 1, 1. This is 1/2 minus 2, 1, minus 1, and minus 3. Okay, it's always better for me also to work it out beforehand so that you don't get lost here. Okay, now let's multiply the first row. 2 times this is what? Everybody please follow. So we are multiplying first row of U with this column, right? This is L, U, X. Now we are doing this. Okay? Okay. So 2 times 1/2 is 1. Then 1 times -2 is -2. So what is the running sum? It's become -1. Then 1 times 1 is 1. So it is 0, right? Good. So let's take this vector. So we found out that this first column is in the null space. Now let's look at the second column. So 2 times, of course, we have to look at the other rows as well, right? So 2 times -1 is -2. And 1 times 1 is 1. So it is, I'm sorry, 2 times -1 is -2. 1 times 1, so it is 1. Running sum is 1. Okay, then 0 times 1. Then you have 1 times 1. So it became 2, right? Or what did happen here? Okay, let me write it. So 2, so we are multiplying this and this. Okay, together. I need you because I don't have the view. Okay, 2 times -1 plus 1 times, this was what, 1, right? 1 times 1 plus 1 times 0 plus 1 times 1, 0, 0, right? So it is -2, and so it is 0, right? So let's multiply also the second row. Second row, if you multiply the second row, what do you get? So second row with the first column here. So it is minus 2. Then you have 2 times, so it is plus 2. It is 0, and the rest is 0, right? And third column gives you 0. So just work it out. You will see that all of these columns are in the null space of A. Did you understand it now? Who understood it now after this example? Good. Okay. Okay, this first one took a bit time. Let's look at the next one. Let's look at left null space of A. Okay. So left null space of A, left null space of A, meaning the set of x's that satisfy this. Okay? So we are looking for set of linearly independent x's that will satisfy this. Okay? And they are the column. And so how do we go about again? X transpose, what is A? It is L times U, right? Equal to 0. Okay? So I can just say that X times X transpose L, I can just call this X hat, right? X hat transpose U equal to 0. Then what do I say? The null space of A, left null space of A is the left null space of, wait a minute. So we will call this Y, and then we say Y transpose, this Y transpose U equal to 0. So this is again, you have to find the left null space of U from this equation, right? Like we did there. Then you solve for Y from this equation. Then you say X transpose L is equal to Y transpose. So and when we look at this, so Y transpose U is equal to Y1 transpose Y2 transpose U11 U12 0 0, right? So this is equal to Y1 transpose U1. This is Y1 transpose U11 U12. This has to be equal to 0 0, right? So this is going to give you, the first one gives you what? U11 transpose equal to U11 transpose Y1 transpose is equal to 0. That means since U11 is non-singular, that means Y1 transpose is equal to 0. Okay? And if Y1 transpose equal to 0, of course, this is also 0. So how do we find Y2? Okay? So you have here then Y is equal to Y1, Y2. There is no condition on Y2. That means Y2 is free variable, right? So how do we pick that one? So you have X transpose L is equal to Y transpose. That means X1 transpose X2 transpose is equal to times L, L11, 0, L21, L22 is equal to 0 and Y2. And Y2 is free. Let me continue this after the break, okay? Let's not hurry it. We will do an example on it also. Let's give a 5 minutes break and come back after 5 minutes. So we said that, let me recap. We want to find the left null space of A, right? We said that we will work with LU decomposition. So we can just replace it with LU. Therefore, X transpose LU is equal to 0. So we call this Y transpose. We rename it. So this becomes Y transpose U equal to 0. You solve this first. Then X transpose L is equal to Y transpose, okay? So let's explore this now. So from here, Y transpose U is, since U is in this partition form, U11, 0, so U11, U12, 0, 0. Here I have Y1 transpose, Y2 transpose. What are the dimensions of this? Again, so this is R by R, right? So this is, we determine U11 from the rank of the matrix, which is rank of U. So this is R, and what is this? M minus R. So we have M rows, therefore this is R, this is M minus R. So this is R, M minus R, this is N minus R, and this is R. Okay, so this has to be 0 for Y. Why does it have to be 0, by the way? Ibrahim, why does it have to be 0? Why am I forcing it to be 0? Because I am looking for the null space, right? I am trying to find out what are the animals living in the null space, right? This is a space, and some animals live there. They are the vectors, right? So you multiply this, you obtain what? Y1 transpose U11, and you multiply with this one, Y1 transpose U12 is equal to 0, 0. So this will give you two block equations. So Y1 transpose U11 is equal to 0. Y1 transpose U12 equal to 0. From here, since U11 is invertible, you have Y1 transpose is equal to 0. And that becomes 0. So there is no condition on Y2. So what does it mean? Y2 is free. You can pick it anything you want, meaning it has to be, so this is R and this is M minus R. You have M minus R, you can pick M minus R linearly independent vectors as your Y2, right? And how do I pick them? I would pick them, of course, identity, right? Anyway, before that, so I have Y is equal to 0 and Y2. Now I come to solve X2, X transpose. X transpose L is equal to Y transpose. Therefore, X1 transpose, X2 transpose, and L is L11, 0, L21, L22. This is supposed to be equal to, now what is 0, Y2. And what do I have? X1 transpose L11, right? I'm multiplying this with this. X1 transpose, then what do I have here? X2 transpose L21. And what is that equal to? 0, right. And the other equation is X1 transpose times 0 plus x2 transpose times L22 is equal to y2, which is the free variable, right? So x2 transpose is equal to, again, L22 is invertible, right? You have this, in L1, you have all these ones in the diagonal. It's a triangular matrix, it is invertible. X2 transpose is equal to y2 L22 inverse. So, let me come to that point now. Let me repeat what I said let me ask what I said 5 minutes ago. How many different ways I can pick y2? It's a free vector with dimension m minus r. Meaning, I can pick them, this m minus r, I can pick them any garbage I want, as long as they are linearly independent, right? But I will be smart. Why should I do unnecessary multiplications? I will just pick it, 1, 0, 0, 0, then 0, 1, 0, 0, right? All the way 0, 0, 0, 1. Meaning I will pick it, I will just stack all of them together, m minus r of them, right? I will take it as an identity. So I will say that my free variables are the columns of identity matrix with dimension m minus r. Okay? So then I will just solve all of these x2s together. Okay, so I make this here so it becomes a matrix. So what does this mean? One x2 I found, I make it one row. Okay, the other one, second row, the other one, third row, etc. I stack them together and I obtain this matrix. This is x2 is equal to L22 inverse. Okay? And from the first one, what do I have? So you have this all in the video. So you have, from here, I have x1 L11 is equal to minus x1 transpose, of course, transpose x2 transpose L21. Okay? So x1 transpose is equal to minus x2 transpose. What is that? L22 inverse. L21, and you multiply with L11 inverse from the other side. That's it. So what is my x? Big X is x1 is this x. Let's write it x transpose. It's better, right? Let's write it as x transpose. So minus L22 inverse, L21, L11 inverse, and you have here I m minus r. That's it. Let's continue our example. Hopefully, we'll understand it better now. So, for the same system, now we are looking for left null space of our matrix, okay? So, what am I going to do? I will just take this, right? I'm looking for L22 is what? L22 is 1. L11 is 1, 0, 1, 0. So 1, 0, 1, 1. L21 is equal to minus 1 and 2. So I will just do that multiplication. So minus L22 inverse is 1, so it is just 1, okay? Times L21 minus 1, 2, and L11 inverse. What is the inverse of that? 1, 1, minus 1, 0. That's it. So let's make this minus 2, so it is 1. So it is 3 and 2. Minus, it says minus 3 here. It doesn't matter. Minus 2, okay? This is minus, yes. Okay. And what is my X, big X transpose now? It is, by the way, how many vectors do I have? So the rank here is 2, right? And what is the dimension of my left null space? M is what? 3. So how many am I going to find? Just 1, right? So it is 3 minus 2, and this is going to be just 3 and 2, this is just 1. So this identity becomes just 1, okay? So the claim is that, so this big matrix is not after all a big matrix in this case, right? It is just a row vector. If you multiply this with this one, you will get 0. Let's see if we do. Okay, multiply this now. Okay, so this with this, what do I get? 3 times this minus 2 times this, so it is 1 minus 1 times that, so it becomes 0. Okay, so first one is 0. Second one, multiply this with the second column. Minus 2 times this is minus 2, and then this is 0. Then multiply this with this one, what do you get? 0, 0, and 1. Okay, then multiply that with this one, what do you get? 0, right? Because first 2 rows will be multiplied by zeros. Do you think I am right, Abdul Fattah? You did not sleep last night. You had exam this morning? Did you understand it? Who understood this? Guys and girls, I'm just doing matrix multiplication here. I'm not doing something new, right? In this board, I'm just doing matrix multiplication. I'm multiplying this X transpose, or this X transpose times A, okay? That means 3 minus 2, 1 times this L. It is 1, 1, minus 1, 0, 1, 2, 0, 0, 1. Okay? Then you have here 2, 1, 1, 1, minus 1, 2, 0, 1, 2, minus 1, 1, 3, 0, 0, 0, 0, 0, 0. So this is what I did. So multiply this with this. So what do I get? Ibrahim, what is it? 3 times this is 3. Minus 2 times this is minus 2. So it is 1. 1 times minus 1 is minus 1. So the result is 0. Okay? 3 times this is 0. Minus 2 times this is minus 2. 0. And so you multiply it with this third column, 0, 0, and 1. But so this becomes 0, 0, 1. If you multiply this with that one, as you see, this 1 just corresponds to all these zeros, and the first 2 rows are multiplied by 0. So the rest is, so it is in the null space. Who understood this now? Good. Okay. Okay, row space of A. This is the easiest one. None of them is difficult, but this just clearly comes out. So row space of A. So we are looking for all linear combinations of the rows of A, right? Remember, this was like x1, x2, x3, xm, r1, r2, rm. So you are just taking all possible linear combinations of R rows of A. This is A, okay, written in row, in terms of row vectors, okay? So since we have A is equal to LU, then you have Y transpose equal to X transpose LU, right? So let's call this Z, okay? So X transpose L, let's call it Z. For every X, Z transpose. For every X, I have a unique Z, and vice versa. Why? Why is that? This has a unique solution. Why is that? Because L is square and invertible, right? It has an inverse. You give me Z, I can just say X is equal to Z transpose L inverse, and vice versa. So I can always, so therefore, since what is the row space of A? It is all possible linear combination of rows of A, right? So if I take, so this is telling, what this is telling me is that if you take all possible linear combinations of rows of U, you will cover the same space. That's what this is telling me, okay? Since there is a one-to-one correlation, therefore, row space of A, which is RA, which is equal to column space of A transpose, is equal to, or equivalent to, not equal, equivalent to, row space of U, okay? That's it. So let's go back to that problem here. So what are the vectors that spans the row space of A? Do I need to do any computation here? Abdul Fattah, any computation needed? So what did I find out? So these two vectors, they span the row space of A. You didn't understand this? Okay, how can I explain that? If I give you this, I ask you, find or generate, okay, this is a better word, generate all vectors in the row space of A. What would you do? You would take linear combinations of the columns of A, right? So you would multiply this with matrices, with vectors from on the right side, which corresponds to taking linear combination of the columns, right? You would take infinitely many different x's, okay? You would take all x's in Rn. So these x's would be where? In Rn. Okay, I would go around Rn and try all possible linear combinations and take them and multiply A with those vectors and get a result. Let's call it y. Okay? So this y would be obtained by taking linear combinations of the columns of A. Right? So here, in the row space, it's the same thing. You have a matrix A, what we are saying is that you take all linear combinations of rows of A. Okay? X is where? X is an m-dimensional space. You take any vector, all vectors in an m-dimensional vector space and compute all possible linear combinations of the rows. And what are you going to get? You are going to get the row space of A. So these vectors, okay? So what is the dimension of this vector? The space that these vectors lie in. That's what we are investigating. What we said here is that since we have LU decomposition of this, okay? And here you can just say X transpose L, you can just rename it as Z transpose, okay? What this is telling you is that since for every X you have a Z, after all you are getting Y's here, right? So instead of trying to take all linear combinations of X and times L and U, it's the same as since you can just, it's the same as taking all linear combinations of rows of U, because there is one-to-one correspondence between the two. Yes, you have a better way of explaining this? Please help me. Yeah, that's what we did.
Clarifies it. Doesn't goes U.
Exactly.
U is like a combination of
Absolutely. Yes. This is what we did. That's why we do Gaussian elimination. We did Gaussian elimination, okay? Exactly. Gaussian elimination, thank you, that's why this U gives you exactly that. Because when you have a large matrix, you don't know which rows will span the row space of that A, right? But since these are all linear combination of the rows, naturally, this U, rows of U, gives you, the first R rows of U gives you the row space of A. Yes, that's exactly what, that's the reason. Because this is, if we were carrying out Gaussian elimination not with rows but with columns, we would have the same thing for column space. But since we are doing it with, we are doing row operations, not column operations, therefore automatically the U, the rows of U, first R rows of U are the basis for the row space. Good for helping me out. Now who understood it? 1, 2, 3. Okay. I don't know what to do. Okay, you have to go through this. Believe me, if you go through this at home, just send me an email if you get stuck, okay? I will help you. Send me questions. Don't ask me what is in the exam. Ask me questions, okay? You have my email. You send me, some of you send me email to ask me when is the exam date, etc. That's posted. Ask me questions if necessary, but I don't know how else I can explain this. This is exactly, this is Gaussian elimination. Gaussian elimination means linear combinations of the rows of A. Therefore, U is a result of those linear combinations, and you are just throwing away the 0 rows, and the remaining rows is, of course, the basis for your row space of A. Okay, the last one, example is there, so there is no computation is needed, so this is the simplest and fastest. Now, the column space of the last example, the last one is the column space of A. So CA. Okay, here we have Y is equal to AX. So remember again, you have here column 1, column 2, column what? N, right? So you have here X1, X2, Xn. You are taking, okay, this is a good way of writing it, X1, C1, X2, C2. I wrote this 100 times, I will write it 100 more times because it is very important to look at this way, okay? You are taking linear combinations of columns of A to get vectors in CA. So this is in CA, okay? You take any x in Rn. This is in Rn. You take anything in Rn, okay? This is in column space of A. Okay? So let's do the same thing. So y is equal to L U x. Let's call ux as y. So, let's call this z. Let me just follow the same terminology. Okay. Before I do that, let me continue like this. So L11, 0, L21, L22, U11, U12, 0, 0. This is x1 and x2, right? So let's first multiply this out. What do we get? L11, 0, L21, L22. And this is U11, x1 plus U12, x2. And this is 0 times this. Basically, what's going on here is this. You start with any x with n-dimensional x in Rn, right? What this is telling you is that what matters there is first R components of it. So you can pick x2 freely, okay? So basically, I can just call this z1. Okay, give me any z1. Okay? I can find it from here. How do I do that? I can just take x2, 0, and x1 is equal to u11 inverse z1, right? So there is one-to-one correspondence. Right? So therefore, the column space of A is just linear combinations of these first two matrices. So column space, a basis, of course. You can find many other ones, but column space of A, which is CA, is spanned by L11 and L21. First two columns of A. Okay? Any questions? So I will stop the lecture here because I don't want to enter. I see that everybody is very tired. And I guess this week is your exam week, so this week I see that everybody is extra tired. Okay?